Start.
All
Okay,
right.
I'd like to welcome everyone to the research session of the symposium. So this is the AI ML track. Again, my name is Hugh Wynn from Rowan University, and I'll be the moderator. And so today we're going to have 5 researchers, each give 15-minute talks on the research involving AI, ML, deep learning. And so let me just lay out some ground rules for the presenters before we start. And so again, the 15 minutes that you'll be given includes Q&A. And so then you're welcome to speak for the entire 15 minutes, or if you want to leave some time for Q&A, you can do that. I'll try to give you a 2-minute warning at the 13-minute mark. So there are no breaks here. So we're just going to go one talk right after the other, and we're going to try and end at 12:30, and we're the last session. So for those in the audience, if you like to ask a question, please post to the chat. And then if the talk ends early, then the presenter can try to answer verbally, or if the talk is over, then hopefully the presenter will answer through the chat to your questions. Okay, all right. Then why don't we go ahead and get started? So our first speaker today is Oliver Alvarado Rodriguez from the New Jersey Institute of Technology. And he's going to be speaking on large-scale graph analytics in Arkouda. So Oliver, it's all yours.
Sounds good. Let me share my screen. So let me start with an introduction. Hi, everyone. My name is Oliver Alvarado Rodriguez. I'm a computer science PhD student at New Jersey Institute of Technology. And I'm here today to present our research on large-scale graph analytics in Arkouda. Providing equal rights in data science is important to increase productivity. The question is, where do we begin? Well, first we need to take away some fear from tech terms such as high performance, parallel, or distributed computing that general data scientists may not be very familiar with. They are just tools that we can all use to increase the productivity of our data science workflows. Then we can take down some of the barriers that can make these tools seem daunting or unattainable. 2 of these are the interface barrier, which involves removing complicated and low-level parallel programming by replacing it with high-level interpreted languages, and the resource barrier, which involves avoiding having to directly utilize supercomputers or high-performance computers, and rather rely on connections from personal computers to supercomputers. Basically, how can we make our interfaces nicer to access powerful resources? Then we need to make the quick and snappy interactive analytics work well with large data sets, which is often referred to as large-scale analytics. The objective of this project is to help create a one-stop solution for non-HPC users who need to perform analytics on massive data sets. We can achieve this with a tool such as Arkouda. The main focus involves creating and implementing some of the data structures and algorithms to provide a vast array of tools that data scientists may use. The framework of implementation is Arkouda, and we are focused on the red circle part here for this project and presentation.
Oh my God.
Why Arkouda? Well, from a talk given by the original creator behind Arkouda, Merrill, we want our data scientists to drive an F-22, sort of say, and execute large-scale code on powerful backends with simple front ends. From the other creator, Reus, Arkouda is a trunk of sorts that can combine a Python front end with a Chapel backend, allowing Python packages to interact with Arkouda and process data in the powerful Chapel backend. You can implement packages and libraries at either end. The main environment setup is nice and simple. You have your user at the front end working with their file or Jupyter notebook and communicating through a ZMQ socket to access all the powerful code at the backend. The Python implementation involves a PD array class, relies on Python to reduce complexity, and can integrate with and use NumPy. This Chapel backend allows for a simple distributed object storage and can run on massively parallel processors, symmetric multiprocessors, clusters, or even a laptop. Chapel is a high-level language with C-comparable performance, great parallelism handling, great distributed array support.
Are you serious?
It's portable. You can get Arkouda from GitHub and take advantage of the Python front end and nice server backend. The links are provided here in this slide with the link to the original software, as well as a link to our implementation, which is this link down here. Arkouda allows us to perform large-scale graph analytics. Why do we use graphs? Well, the information they can abstract, such as social networks, can provide useful information for researchers from all domains. As graphs become huge, computing at a local laptop level becomes close to impossible. Therefore, data structures and algorithms are needed to handle massive data sets. Our contributions include an array-based data structure, a breadth-first search implementation, and a triangle counting implementation. Pictured here is our implemented data structure that is composed of 4 arrays for the directed case and 8 arrays for the undirected case. The edges are sorted, and the directed edge exists from the vertex source SRC array to the destination DST array. These arrays allow for a search complexity of constants big O of 1 time, as any of the n vertices can find its neighbors using the NEI and STR arrays. The undirected case has some additional reverse arrays to enable this constant time. The raw data is only stored at the backend. Let's look at the image on the right. Let's say we have one vertex index array, STR. At index 50, we have the value 1000. And another vertex index array, NEI, at index 50, we have the value 3. It means that for the given vertex 50, the edges starting with vertex 50 are stored in the edge index array starting at position 1000. And there are totally 3 such edges. If there is not any edge from vertex I, we will let STR at I be equal to -1 and NEI at I be equal to 0. In this way, we can directly search the neighbors of any given vertex. Graph sketches can be used to run analytics on a smaller version of a much bigger graph. The user can pick a shrink factor, which will generate a new graph that is 1f of the original graph. Multiple independent hash functions were utilized for 3 different partitions to generate better results. Each of these parts make up 1/3 of the 1f sketch. A regression model was then built from experimental results to predict the number of triangles in a graph. Here's an example of the BFS problem. You start at a source vertex and then return a depth array that shows at what level each of the following vertices are in comparison to the source vertex. So our input is a graph. Our source vertex is 0. We perform BFS. The green values are the depths. And our output is a depth array, in this case D. Each index of this D corresponds to a vertex, and each value is the depth of that vertex in relation to the source vertex. So index 0 represents node 0, which the depth from itself is obviously 0. Then index 1 represents vertex 1, and its depth is 4, and we count the edges. 1, 2, 3, 4. We're 4 away from the source vertex. Now we show how parallel BFS works. Each of the ovals can be visited at the same time by the same locale, since no information is needed to be known between the vertices in that oval. BFS is a good problem to tackle with parallel solutions due to its asynchronous nature. Pictured here is our BFS algorithm to generate the depth array at what depth each vertex is found compared to the starting vertex. It exploits Chapel's easy distributed and parallel computing language constructs that are shown in red to return the final depth array. Chapel provides a vast selection of data structures that can be used to store vertices at the current frontier during BFS execution. They include set, disbag, and domain, which were all compared to each other. BFS is usually useful for finding shortest paths, for psychodetection, and for other problems, which are all really good problems to tackle when you're dealing with graphs. To show the flexibility of Chapel, we compare the different data structures in Chapel to one another to show the speedup that can be obtained from specifically optimized data structures in code against just picking whatever the first data structure or code structure may be. As we see, our final optimized version is much better than all the other implementations pictured here. The Delani Graph with 2 or 3 million edges only took 1 second to return the BFS depth array. The speedups are shown in the table on the right, with the optimized code running 8 times faster than the slowest. This shows that we can take advantage of Chapel to improve algorithm design productivity. Now pictured here is a general outline of a triangle counting problem. Each triangle is counted and the integer value of the number of triangles is returned. This is our input. Then we count the first triangle, the second, the third, the fourth, and the fifth. You can see that some to get the final triangle count 5. You can see that some triangles may share edges and nodes. A triangle counting algorithm needs to consider triangles that may share an edge and up to 2 vertices. So these triangles here both share an edge, and over here too. Shown here is our triangle counting algorithm that was developed, which works for either a full graph or a streamed graph. A graph stream, as we mentioned before, is a certain large graph shrunken down so the algorithm executes more quickly with minimal loss in accuracy when comparing predicted triangle counts to true triangle counts. Chappell's distributed constructs, pictured in red, were exploited as well to split up the work amongst locales and amongst the multi-cores in each locale to return a final triangle count. Triangle methods help to provide useful information about graphs, such as small communities, friendships, or collaboration networks of size 3 that may exist. Here are 2 graphs showing the most important triangle method results. The y-axis is a relative error of how far off the number of triangles counted were compared to the actual true count. The formula above were the regression models used to predict the triangle counts, where EH over here is the exact count of triangles from the head partition, EM from the mid partition, and ET from the tail partition. The A, B, and C were fitted dependent on the trained model. When graphs were shrunken down, the error stayed relatively low. The mean error stayed relatively low, under 5% for normally distributed graphs, and under 10% for power law graphs. And all the max values stayed within the 25% range. Here's a table showing the speed up that is acquired when a graph is shrunken down. These speed ups, some of them close to 30 times faster, yield very little losses in accuracy, as we saw in the previous slide. Sometimes they may have to be adjusted to minimize the loss. The largest graphs, LJ and YouTube, shown in red there, with 30 to 60 million edges each, had little losses in accuracy with huge speed ups in execution time. So you can see for LJ, the stream time took 397 seconds and the exact time was 6,937 seconds. 397 seconds is about 6-7 minutes, and 6,937 seconds is about 2 hours. So really shrinking it down by a large factor with minimal loss in accuracy helps to speed up execution time. In conclusion, Arkouda proves to be a useful tool to perform large-scale graph analytics with the ability to implement graph and other algorithms rather easily. It allows for a friendly user interface with a powerful supercomputing backend if necessary. Our plan for the research includes implementing more graph algorithms and optimizing them for parallel and distributed computer systems. We can also look at other problems of interest and switch over from specific large-scale graph analytics to just regular large-scale data analytics. And that's it for my presentation. I can take any questions now.
Thank you, Oliver.
No problem.
Thank you. Okay, well, I don't see any questions, Oliver. And so thank you again.